Okay, let's go ahead and get started. Today I want to wrap up our discussion of dimensional analysis. Which, as I remind you, is the tool by which we can all pretend to be much smarter than we actually are. Because dimensional analysis is the tool which allows you to constrain the possible equations of motion of physics really without doing any work whatsoever. So let me just remind you that, of course, every physical law has to relate quantities of the same dimension typically, in this course, we'll be working in terms of what are known as the three basic dimensions, length, time, and mass. Although, in other situations, it might be appropriate to introduce other so-called dimensions that are independent of these. For example, in some systems of units, people talk about the charge of a particle as having units that are not constructed out of these three basic units. One can also define temperature, which is not related to these three basic units, and so on and so forth. For example, if you read the recommended reading from this book on street fighting mathematics, you'll see the use of dimensional analysis in economics, where money is a dimension, a different sort of dimension. And so there are all sorts of situations where dimensional analysis is useful, but we'll be considering today just those physical situations where we're considering quantities built out of these three basic units, length, time, and mass. And the two basic principles that we use in order to constrain our possible laws of physics are, first, what I would call the basic principle of dimensional analysis, which is that in any physical situation, you should write down all of the various dimensionless quantities that are relevant for describing the physics of some problem. And any one dimensionless quantity, should be a function of the others. This is just the basic principle of dimensional analysis. And the second, which is not so much a principle, but rather a rule of thumb, is that any function of a dimensionless quantity is typically of order 1. So this second rule is not so much a law of physics as a general principle that we can use to estimate the size of effects in physics. It's not always true. For example, the number 5 is of order 1, okay? But the number e to the e to the e to the e to the 5 is not of order 1, okay? So one has to take this rule with a bit of a grain of salt. But generally speaking, if you have a physical situation where you don't know what's going on and you want to try and estimate the size of the effects of some principle, then this principle of order of magnitude estimates is usually the best place to start. And generally speaking, if you come up with an example where this rule, this principle number 2 fails to apply, there's usually a very good reason for it. So last time we had a guest lecturer, Guy Moore, who hopefully used these basic principles to give you several examples of physical situations that we can think about and make estimates based on these two principles. And what I would like to do today is to take this one step further, and I would like to use this to estimate the size of corrections to Newtonian physics from quantum mechanics and from relativity. So I remind you that, of course, our goal and in this course is to understand the modifications to Newtonian dynamics that one has to consider in special relativity and in quantum mechanics. And before even diving into any details, what I want to do is to show you today how, without even knowing the theory of special relativity or the theory of quantum mechanics, one can use dimensional analysis to guess what the basic size of these effects will be on various different sorts of physical situations. Maybe before I go into any details, I should pause and see if there are any questions and if the general idea is clear to everyone. No questions? Feel free, of course, to interrupt with questions at any time. Again. So, the basic parameters that control the sizes of relativistic and quantum mechanical corrections to Newtonian physics are the speed of light and Planck's constant. So relativity gives corrections to Newtonian physics parameterized by the speed of light, typically denoted c, which is a velocity, and so it has units of length divided by time. And in quantum mechanics, the size of corrections are governed by Planck's constant h bar, or Planck's constant h, whose units are mass length squared divided by time. So, whereas it's easy to understand why length over time has a physical interpretation in terms of velocity, the combination mass length squared divided by time is a little harder to interpret physically. But you can think of it as energy times time. Remember that kinetic energy is 1/2 mv squared, which means that energy has units of mass times velocity squared, or mass times length squared over time squared. So that means that energy times time will have units of mass times length squared divided by time. So for example, if you were to study a physical situation and say, let's say I take this chalk and I throw it across the room, and you want to measure the integrated amount of energy contained in this chalk between 1 second and 2 seconds after I throw it across the room, that's a quantity that would have the same units as Planck's constant. Okay, there's a question.
Yeah, it's also a unit of angular momentum too.
Correct. Correct. So there are many quantities which all have the same dimension. It has units of angular momentum. Okay. How can you see that? What is angular momentum? Well, as you hopefully remember from your mechanics class, angular momentum is position cross velocity. Position cross momentum. So it has units of position times momentum. So it's length times momentum. And what is momentum? Momentum is mass times velocity, m times L over t. So momentum times position has units of mass length squared over t. Good. Okay. And so in order to estimate whether relativity or quantum mechanics is important, the question that you want to ask is whether the typical dimensionful quantity that you would construct in a given physics problem is of order these basic parameters c and h. So, for example, for a given physical system, if you compute the velocity of all of the various parts of that system, and you find that the velocity is much less than the speed of light, then that implies that relativity is negligible. For the example of the piece of chalk that I throw across the room, presumably I throw it at a speed much less than that of light, which is good because we don't need to use relativity then to determine who that piece of chalk will hit. And second, of course, if you compute, say, the mass of that piece of chalk times its momentum, or the energy of that piece of chalk integrated over time, to obtain something with dimensions of mass times length squared over time, and if you compute that, and you find that it's much, much greater than Planck's constant, then that implies that quantum mechanics is irrelevant. Quantum effects will be negligible. And one can even go one step further, as we will do in just a minute, and use this principle not just to say that these effects are negligible, but to give a numerical, albeit order of magnitude estimate of the sizes of these sorts of effects. I should mention, though, as an aside, which is that there is a third basic quantity, or a third basic parameter, which we will not talk quite as much about in this class, but which governs the size of corrections to Newtonian physics, and that is Newton's constant. So whereas special relativity is governed by the speed of light, quantum mechanics is governed by Planck's constant, the effects of gravity are governed by Newton's constant, g. And Newton's constant has dimensions of mass times length cubed times t squared. So there are a variety of different ways of checking that this is the case. So one way of checking that this is the case is to remember our favorite equation in Newtonian physics, F equals ma, and remember what the Newtonian force is for two objects that are attracted by the force of gravity, which says that the force is minus Newton's constant times the product of the masses. So let's just say that they have, so something of dimension mass squared divided by their distance squared. And so just equating the top and the lower expressions here, and remembering that acceleration has dimensions of length over time squared, because it's the second time derivative of a position, allows us to determine the dimensions of Newton's constant, which I hopefully got correct here. Wait, did I get them correct? I got them. Wait, no, it's the inverse of. Wait, did I get them correct? Okay, exercise. Someone derived it. Yeah, there's a net minus sign there somewhere. So it's 1 over mass. Okay, good. Let's do this in real time. It's got dimensions of length cubed, and it's got dimensions of 1 over time squared. Clearly, I copied this down in my notes incorrectly. Right? Everyone with me so far? Okay. Good. Right? You can see what's 1 over mass because there's a mass squared on one side and a mass on the other side. It goes like length cubed because acceleration goes like length, and we have to multiply through by a factor of r squared on the top and bottom sides of this equation. And it goes like 1 over time squared because of, well, acceleration, it goes like 1 over time squared. Any questions on that? Even I can make mistakes. It happens every once in a while. Okay. And your job as diligent students is to correct me and complain when I do. Yes, questions?
So if we mention the first two and then this one, is it like this one interconnects?
No, the way that I would say it is the following. There are 3 sort of basic effects that we might be interested in describing. There are the effects due to gravity, the effects due to quantum mechanics, and the effects due to relativity. And the size of these effects is governed by the size of whatever dimensionful quantities are in the physics of the situation that you're studying and the size of these basic parameters. So for example, if I were to study a pendulum, as I will in just a minute, and look at the typical velocity of the pendulum, I could compare that to the speed of light, and that would give me an estimate of the size of the corrections to the motion of that pendulum due to relativity. And I could also compute not the velocity of the pendulum, but rather, say, for example, the angular momentum of the pendulum, and that would give me an estimate of the size of the corrections due to quantum mechanics. Yes?
What if all three effects are negligible? What would you call that?
I would call that Newtonian physics. Okay. I mean, I'm starting from the point of view that we know Newtonian physics. That may or may not be the case. But for the purposes of this class, we assume that you all know Newtonian physics. And so that's not to say that you can solve the double Atwood machine or whatever the hell that is. But we're starting from the point of view that you're John Clerk Maxwell or whoever you are. You know Newtonian physics, and we are understanding the sizes of corrections to Newtonian physics due to these three basic effects. And just as a bit of a aside, I should say that we, whereby we, I mean we as a species, we as physicists, understand well physics where any two of these effects namely relativity, quantum mechanics, and gravity are important. So, for example, if none of the effects are important, well, that's what we call Newtonian physics. In the absence of gravity. If only Newton's constant is relevant, if only gravity is constant, well, that's what we call Newtonian gravity. Okay. You guys know that one too, actually. You know, orbits of the planets, stuff like that. If only the speed of light is relevant, if only relativity is relevant, that of course is special relativity. If only Planck's constant is relevant, then that is quantum mechanics. And we also understand well the theories where any two of these are relevant. So if both relativity and quantum mechanics are relevant, then that's a theory that we call quantum field theory, which I alluded to in the first lecture. And that is the theory of the standard model of particle physics. So, indeed, perhaps by the end of this class, I will explain to you why it is that when both relativity and quantum mechanics are important, one is forced to study particle physics. If both gravitational and relativistic effects are important, then we have the theory known as general relativity. And if both quantum and gravitational effects are relevant, but relativistic effects are not relevant, then we have a theory that nobody actually really studies very much, because there are almost no physical situations that I can think of at least where this theory would be important. But this is a theory that one could study, which would be quantum Newtonian gravity. And the only theory that we don't understand is the one where all three effects are important at the same time, which is the theory of quantum gravity, which is a mystery wrapped inside an enigma. And beyond the scope of these lectures. Questions? Okay. So enough of this general nonsense. Let's go and understand a couple of examples. So let me start out with an example that I understand that Guy told you about on Friday, which is that of a pendulum of mass L, mass M, and length L in a constant gravitational field. Say, the one in this room. So the acceleration due to gravity is then roughly 10 meters per second squared. 9.8 is equal to 10, by the way. So one can then, if one considers the motion of this pendulum in a constant gravitational field, then you could go ahead and estimate the typical velocity of this pendulum and compare that to the speed of light. So, for example, you could imagine a configuration where the pendulum is started at rest at an angle theta off of vertical, and then it's allowed to swing back and forth. And you could compute, of course you know how to compute this precisely, but we're not doing precise computations. You could imagine estimating the velocity of this pendulum as it passes through the origin as a function of these basic parameters. And the important observation is that the angle theta is dimensionless, so that the velocity of the pendulum will, in terms of dimensionful parameters, only be determined by this mass, length, and the gravitational acceleration, g. And so then we could construct out of those three dimensionful parameters, m, l, and g, something with dimensions of velocity. And if you think about it, the first thing that you notice is that, g has dimensions of length over time squared. So that means that the velocity has to be completely independent of the mass of the pendulum. Because out of three quantities of dimensions mass, length, and length over time squared, the only way you can get something with dimensions of length over time is if you don't include the mass of the pendulum. So you automatically conclude here, for example, that all of the properties of the motion of the pendulum are independent of the mass of the pendulum. Okay. That's already a very important statement. It follows just from dimensional analysis. Now, I'm neglecting here things like air resistance and so forth, but if you like, I encourage you to try and use dimensional analysis to estimate the size of the effects due to air resistance. Okay. Maybe you'll have to use Wikipedia. But the typical velocity of the penguin, of course, would be the quantity constructed out of the length and this gravitational acceleration g, with dimensions of velocity, which, if you think about it, has to be, the only quantity you can make is the square root of g times the length of the pendulum. So that means that special relativity is negligible if the square root of GL divided by C is much less than 1. The velocity is slow compared to the speed of light. And we can take this observation one step further and estimate the size of the corrections due to relativity. So, for example, let's estimate the period of the penguin, estimate the corrections to the period of the pendulum due to special relativity. So, now, without including special relativity, you know that the period of the pendulum, so So let's say the time it takes the pendulum to go through one of its cycles from theta to minus theta and then back to theta again will, just by dimensional analysis, have to go like the length of the pendulum divided by the acceleration g to the 1/2 power. Why is that? Well, g has dimensions of length over time squared, so L over g has dimensions of time squared, and this is the quantity with dimensions of time. And so, in particular, if you want to compute the period of the pendulum as a function of the angle theta that you start this pendulum swinging at, then you would expect that the period of the pendulum would be some function of theta. Okay. Now, it's a function of theta that you can compute. It's some integral, but I'm not interested in computing it exactly for you. I just want to provide an estimate. And then you could imagine adding the effects of special relativity, and you would get some sort of corrections to this formula. Now I would like to estimate the size of these corrections. So this is how I'm going to do this. What I'm going to do is I'm going to remember that the basic principle of dimensional analysis states that in some physical system, we should be able to write everything in terms of dimensionless parameters, and any one dimensionless parameter should be a function of the other dimensionless parameters in the physical system we're studying. So, for example, time itself is not dimensionless, but remember, time times the square root of g over length is dimensionless. Okay. And once special relativity is taken into account, it should be given by some function f of both the initial angle that we start the pendulum at, as well as the dimensionless parameter, square root of gl over c, which describes the strength of the effects due to special relativity. And theta is of order 1. But if I consider a pendulum whose motion is much less than that of the speed of light, then this dimensionless parameter here, root gl over c, should be very small. So I'm using the symbol f here to note two slightly different things, so that could get a little confusing. So let me call this function f up here. I'm not going to call it f. What should I call it? I'll call it tau, because tau is like a t. So because that parameter, root gl over c, is very small, we could then imagine taking this function f, and we could expand it in powers of root gl over c, just by doing a Taylor expansion. And so we would get some function of theta times root gl over c to the 0th power, plus a different function of theta times root gl over c to the 1st power, plus another function of theta times root gl over c squared, and so on and so forth. And if this pendulum is moving slow compared to the speed of light, then this Taylor series provides a very good approximation to the behavior of this pendulum. And moreover, using our principle of order of magnitude estimates, we would guess that f0, f1, f2, and so forth are all of order 1. And moreover, we know exactly what f0 is. f0 is the thing which describes the period of the pendulum in the absence of special relativity. So it's just what I called tau up above. It's f1, f2, and so forth that describe the corrections due to special relativity, so that the period of the pendulum including the corrections due to special relativity, should be the square root of L over G times whatever answer you get without including special relativity, plus something of order 1 times root GL over C, plus something of order 2 times root GL over C squared, and so on and so forth. Where F1, F2, and so on are all of order 1. So this tells us the typical size of effects due to special relativity on the motion of a pendulum. And if you like, I encourage you to go ahead and compute numerically the value of root GL over C for your favorite pendulum. It's going to be very small. For a grandfather clock, I can't imagine that it would be more than 10 to the minus 8 or 10 to the minus 9. And so this tells you that the typical size of the corrections due to special relativity to the period of your grandfather clock will be of order 10 to the minus 8, say. So you can tell then how many seconds it would take before your grandfather clock would acquire roughly 1 second of error due to the effects of special relativity. It might be 10 to the 8 seconds, something like that, within an order of magnitude. In fact, however, it turns out that in special relativity, that estimate is not quite right. So in special relativity, it actually turns out that F1 is equal to 0, and that it's only F2 that is of order 1. So in fact, I misspoke earlier. The corrections to the period of a grandfather clock due to special relativity would be of order 10 to the minus 1 part in 10 to the minus 16. And in fact, and as I mentioned earlier, whenever this order of magnitude estimate is wrong, that usually means that there's something special going on. And it turns out that there is something special going on in special relativity, namely that there's a symmetry of the pendulum problem which prevents you from having this term F1 that I wrote down. Anyone want to guess what that symmetry is? Well, I'm not going to tell you the answer. You can come and ask me later if you want. Any questions on this basic idea? The nice thing about this is that it allows you to say things about special relativity without understanding anything about special relativity. Okay. Now, in the case of special relativity, that's not so important because you are actually capable of understanding special relativity. So if you wanted to, by the end of this course, you could go ahead and compute F1, F2, and so forth completely analytically as functions of theta. However, for other theories that you don't understand, or for theories that nobody understands, this is a very useful set of ideas to allow you to estimate the size of these effects. Nobody understands what the theory of quantum gravity is, but we can still use this to understand what sort of effects it will give to physics that we do know. Okay, there was a question in the back. Yes? Yes. So indeed, the symmetry that protects Newtonian physics from getting the F1 corrections is in fact what's called time reversal symmetry. It's the symmetry that says that every physical situation has to be, let's put it this way, you can run any physical process backwards or forwards and it will still be consistent with the laws of physics. And so this parameter root GL over C that I have written down here is the velocity over C. Okay. And this guy has to be invariant under V goes to minus V. Okay. So it's a Taylor expansion, but it has to be a Taylor expansion of an even function in root G over C. So that's the secret answer to that question. So generally, the lesson is that if you do this order of magnitude estimate and you discover that you're wrong, there is some sort of principle at work, some sort of physical principle is at work, which is explaining why this order of magnitude estimate is wrong. And if you estimate that something should be of order 1, and you find that it's exactly 0, then it's almost always because there's some symmetry principle at work, which is causing this. So, yes, question?
Would it make sense to go to the maximum angle to which extent it makes sense and like go to the maximum speed. It could, like,
Yeah.
go to a
So for example, you could take the pendulum so it's perched up at the top in a very unstable way, and that would be the maximum speed. That would give you some factor of order 1 from a typical speed. Okay. I'm neglecting all factors of order 1. You could, of course, consider that situation if you like. Let's do a slightly more interesting example. So, quantum mechanics. Now, you know very little about quantum mechanics, presumably. But one of the things that that is true about quantum mechanics is that it applies to pendulums. So let's estimate the size of quantum effects to the motion of a pendulum. Now, I don't want to explain to you all of quantum physics in order to do so. But one thing that is true about quantum mechanics is that in quantum mechanics, everything is a little bit jittery. Okay. So it's impossible to have a pendulum that is exactly hanging at rest in quantum mechanics. In quantum mechanics, the pendulum is forced to acquire some sort of motion. So it is impossible to have an object completely at rest in quantum mechanics. And so since no object can be completely at rest, in quantum mechanics, what is the minimum possible energy of this pendulum due to quantum effects? Now, there's a whole deep theory of quantum mechanics involving Schrödinger's equation and so forth, which would allow you to solve this problem exactly. But using dimensional analysis, we can just figure out order of magnitude what the answer is. So, again, the question that I have posed here is to estimate the energy of the pendulum. And I remind you that the basic parameters that we have to play with are the mass of the pendulum, the length of the pendulum, the acceleration due to gravity, which is the length in units of time squared, and Planck's constant, which has units of mass times length squared over time. So there are two dimensionless ratios that we can construct. So without quantum mechanics, the only quantity we can construct with dimensions of energy is, well, energy has units of mass times length squared divided by time squared. So that's mLg without quantum mechanics. And what is the quantity with units of h? So h has units of length times time. Okay. And we saw that time has units of the squared of length over g. So the only quantity with units of energy times time will be mLg times the thing with units of time, which is the squared of L over G, which is M L to the 3/2 G to the 1/2. So quantum effects for a pendulum are negligible if mL to the 3/2 G to the 1/2 over Planck's constant, sorry, I keep drawing H bars here. I haven't told you what H bar is yet. Over Planck's constant is much greater than 1. So this is the principle that allows us to tell whether quantum mechanics is going to be important or not for the motion of this pendulum. If m L to the 3/2 g to the 1/2 is much, much bigger than Planck's constant, then you don't really have to worry about quantum mechanics. Nevertheless, we could estimate the size of quantum effects for the pendulum. And in particular, we could ask what the minimum possible energy is that this pendulum could have in quantum mechanics. So if you don't include quantum mechanics, then the only quantity with units of energy is mass times length times g. But if you do include quantum mechanics, then there are now two quantities with dimensions of energy that we can consider. And so we can go ahead and use our dimensional analysis principle, which says that in any situation where you have some number of dimensionless quantities, any one of them must be a function of the others. So the quantity E, the energy of the pendulum, over mLg, is a dimensionless parameter. So it must be a function of the other dimensionless parameter in the game, namely mL to the 3/2 over g to the 1/2 over h. Or I'll write the inverse of that dimensionless quantity, h, mL to the 3/2 g to the 1/2. Okay. So if it's a function of, if mL to the 3/2 g to the 1/2 over h is dimensionless, then so is its inverse. And why have I written its inverse here? Well, if mL to the 3/2 g to the 1/2 over h is very big, then its inverse is very small. And so again, we can Taylor expand. And what is it? Well, it'll be some number f0 plus f1 times h over m L to the 3/2 g to the 1/2 plus higher and higher order corrections in a Taylor series expansion in that dimensionless parameter, where we expect that f0, f1, and so forth are all of order 1. Now, yes, question?
How do you know how many terms of the expressions?
Well, it depends really on the physical situation that you're considering. If you're considering your grandfather clock, then this parameter h over m L to the 3/2 g to the 1/2 is absolutely tiny. Okay. And so it depends how accurate you want to be about parameterizing the corrections to quantum mechanics. If you only want to build a clock that works, then of course you don't need to consider quantum effects at all, and we would only be interested in the term f0. Because what is f0? f0 is the answer that you get without quantum mechanics. Okay. And what is the minimum energy of a pendulum in classical physics? Well, it's 0, okay, because the pendulum is at rest. So f0 is the minimum energy of the pendulum in classical physics, which is 0. So you can always determine the first term in this Taylor expansion by comparing with physics that you already know. And in quantum mechanics, we now have a prediction, which is that the minimum energy of a pendulum due to quantum mechanics is given by that f1 term. So I'll multiply both sides by mLg, and we find that the minimum energy of the pendulum is h times the square root of g over L. Times something that's of order 1. That's why I write a little squiggly line instead of an equals. And indeed, this is true. It's a true statement about physics. There's a few really interesting things I want to point out about this formula. The first is that it's independent of the mass of the pendulum. Just as in Newtonian physics, if you were computing the period of the pendulum, it turns out the answer is independent of the mass of the pendulum. This is Galileo's famous observation that you can drop two things of different weights from the same height, and they'll both hit the Earth at the same time. We're now saying that there's also a quantum version of this, which is that the energy of the pendulum is also the energy of the minimum energy configuration of the pendulum in quantum mechanics is also independent of the mass of the pendulum. And what I want to do now is combine this with our earlier observation that the time it takes the pendulum to go through one complete swing, so remember the time it takes the pendulum to go through one complete swing was the square root of L over G. So there's another expression for this formula, which is that E is roughly Planck's constant times the frequency of the pendulum. And this sort of formula, where an energy is Planck's constant times a frequency, will appear all over the place in quantum mechanics. For example, the energy of a photon is Planck's constant times the frequency of that photon. And we're now seeing that that can also just be regarded as a consequence of dimensional analysis. There was a question in back. I only have 1 minute left. So let's just go ahead and do that dimensional analysis for the photon. So let's ask another question. So what is the energy of a photon of a given wavelength? Okay, I like this example because it involves both special relativity and quantum mechanics. What's that? Sorry.
Didn't you just say it before?
Yeah. But I'm going to derive it using dimensional analysis. Okay. Yes. So why does it involve both quantum mechanics and special relativity? Special relativity involves going at the speed of light. Okay. What is a photon? A photon is a quantum of light. You don't know what a quantum is yet, but you know that it's something involving quantum mechanics. And light, well, what is light? Light is something that travels at the speed of light. So special relativity better be important. Okay. So what are the basic quantities that we have? We have c, which goes like length over time. And we have Planck's constant, which goes like mass, length squared over time. And we have a wavelength, lambda, which goes like length. Okay. So that means that the energy of the photon, well, it has to go like mass, length squared over time squared. So in order to get the mass dimensions right, this has to be linear in Planck's constant, right? Because that's the only thing which has dimensions of mass. And then in order to get the L squared over T squared to work out, we have to have the c times the wavelength in the denominator. So the energy of a photon of wavelength lambda is h over c lambda, or if, as was already noted, you define the frequency, omega, of the photon to be 1 over c lambda, then this is h bar for h times omega. Okay, so, yes, question?
Instead of doing L squared by T squared as over C lambda, why didn't we not just do S and C squared? C squared in the sense of L over G.
Let's work. You want to use c squared instead of c lambda? You'll be off. You'll get the powers of L right, but you'll get the powers of T wrong. Let's go through it. Oh, did I write the C in the wrong place? Oh, you're right. I did write the C in the wrong place. Sorry. This is what happens when I teach 2 classes in the same day. Good. Thank you. I'm very disappointed in all of you for letting me go that long with such a stupid mistake. I expect better from you in the future. Good. Okay, it's time for me to end. So let me end by posing you a question. Compute the wavelength of a photon or let's see, how should I say this? Compute the wavelength, at what wavelength, here, let me say it slightly differently. Let me say this differently. Okay. At what wavelength will a photon collapse into a black hole? I've given you all of the information you need to answer this question, up the order of magnitudes. So do it. In fact, it's such a good question, I'm going to put it on the next problem. Okay, see you guys on Wednesday.
So I made it to quantum theory.
What's that?